So these are exciting times that we're living in. And we're on this epic journey of human discovery, finding out about the universe. And this is one of my earliest memories, actually. This is a picture that was taken on the surface of the moon by the first people who walked on the surface of the moon. So the picture was actually taken by Neil Armstrong, who you can see reflected in Buzz Aldrin's helmet faceplate. And this is really exciting, and it has a current Open University connection as well, because we enjoyed about a month ago a visit from space royalty. Andy Aldrin, who's the son of Buzz Aldrin, visited us here at the Open University, and he is sort of, in a sense, following in his father's footsteps. He's very interested in space, he's very interested in education, and very interested in space entrepreneurship, and all of those things link up with things that we're interested in doing here. So we're living in very exciting times still. Now, getting to exoplanets, back in 1969, we really didn't know whether the planets in our solar system were completely unique in our galaxy. We didn't know if generally stars are accompanied by planets. And this was a viable theory for how the planets of the solar system were formed back in 1969. Planet formation might have required a very rare and unusual event, like two stars almost colliding and pulling material from the outer layers of the star, which then coalesces to form the planets. And if this was indeed the way planets were formed, then our own solar system could have been completely unique. The sun might have been the only star of the billions and billions of stars in the galaxy which actually had planets. And this was actually a viable picture until quite recently, until about the 1990s. We now know that actually planets form with stars with no special requirements. And in fact, the laws of physics insist that angular momentum has to be conserved. So as the star collapses, you get this disk of material forming, and the planets naturally form under their own self-gravity out of that disk. So we now know that planets form with stars with no special requirements. So we expect that when we look up into the night sky and we see stars, each of those stars will actually have planets orbiting around it, or there's a very good chance that it will do. I should also say, this is not an astronomical image. This is an artist's impression of what a planetary system forming around another star may look like. And we very rarely, literally, get pictures like this in astronomy. We have to use indirect inferences to work out what's going on, and then we talk to artists who make these beautiful pictures. And there is a danger that when we just sort of send these to journalists, they're presented as though this is actually what the telescope saw. It's not. So it's quite important to bear that in mind. And if you zip backwards and forwards there, you can see, as well as learning a lot about science, our scientific visualizations have improved enormously as well in the last 50 years. And I think there's an awful lot of graphic artists doing really beautiful things that people 50 years ago would be very, very impressed by. So we know that there are lots of planets orbiting other stars in our galaxy. And we know that because we've found about 4,000 of them. And statistically, by scaling up where we've got information, having looked for stars in detail, we know that there are many, many planets orbiting other stars in our galaxy. And in fact, the galaxy contains more planets than stars. So that's a lot of planets. The giant planets, planets like Jupiter, are the easiest to find for obvious reasons. They're bigger, they're brighter, they have more of an influence on their surroundings. But we do know that there are many, many Earth-sized planets in our galaxy. So small, presumably rocky planets like the Earth are actually more common than giant planets. So this is really quite exciting, and this is where the Star Trek aspect of my title comes from. As we find out more and more about the contents of our galaxy, more and more it seems to resemble the galaxy that Captain Kirk went exploring on this TV series back in the 1960s, which was another one of my earliest memories. And myself and many people my age used to negotiate very hard with their parents to be allowed to stay up to the end of Star Trek, which was, yeah, it sort of bordered bedtime. So this is a picture of what the galaxy and human exploration of the galaxy might have looked like about 50 years ago. And one of the things that I like about the lower picture is that even the alien kind of looks like a middle-aged white guy, which, yeah, sort of was the worldview back in the 1960s. And more recently, there's a little bit more diversity and a little bit more imagination. So this is a still from a recent film, Star Wars: The Force Awakens, and you can see here the two major characters included are different demographically. Women are allowed to take part in the adventures now, and people of colour are allowed to take part in the adventures now. And I think that's a good thing. I think in the last 50 years, I wouldn't say that's directly the influence of the OU, but I think the OU has helped. We're open to people of all kinds, and that's good. So I'm now going to move into sort of talking in a little bit more detail about stars and planets. And as Dave foreshadowed, I'm going to talk about transiting planets, planets that happen to be lined up so they pass between us and their host star from our point of view here on Earth. And those are special because we can learn more about those planets than we can about planets that are not lined up in that way. So the first thing that I should say, and probably everybody here knows this, but I'll say it anyway, just so we're all on the same page, is that stars are much bigger and much brighter than planets. And as an astronomer, if you're working on planets, that's a little bit of a nuisance because astronomers work with light. And so it's very, very difficult to detect planets because they always come with a star which outshines them. So it's really hard to detect planets. And Dave mentioned it's quite hard to see Mercury. Well, it's much, much harder to find an exoplanet because it's much, much further away. And from the distance we're viewing it, it completely overlaps its host star in most cases. So stars are easy to study, planets are difficult to study. And the graph sort of says the same thing as the words, but it says it in a more quantitative way. So in the optical light that our eyes are sensitive to, the sun is about 10 billion times brighter than the Earth. So that's what we're up against as astronomers. And in fact, what we do is a very clever trick. Rather than looking for the light from the planet, what we do is we indirectly detect and characterize the planet by looking at the effect that the planet has on the light from the star. And the easiest way to do this is to use the transit method. So if you simply collect the light from a star and measure its brightness, what you will find is if that star happens to have planets that are oriented correctly, so the planets pass in front of the star, every time the planet comes round, you'll see the star get slightly fainter as the planet gets in the way and blocks some of the starlight. And you see this happen regularly, and that immediately tells you how long the planet takes to complete one circuit around the star. So it tells you what the planet's orbital period, or equivalently, what the length of a year is on that planet, how long it takes to go once around. So this is really very simple. And as a scientist, it's always really nice to work on things that are very simple because it gives you a bit more confidence that you're getting things right because you can actually understand what you're doing in detail. So the planet detection by transits is a really lovely method, and it also gives us a lot of information about the planet. It's actually the only way we can directly measure the size of a planet outside our own solar system. And you can do that simply by measuring how much light you've lost when the planet gets in the way of the star. So it tells you the size of that black circle relative to the size of the white circle. And we all know that the area of a circle is pi r squared, so that tells you immediately how big your planet is. So that's great. And you can also learn other more detailed things like exactly how lined up is the orbit. You can actually tell by the shape of the dip whether the planet is sort of going across the bottom of the stellar disk or whether it's going across the middle of the stellar disk. And that would give you a different detailed shape of that dip. So transiting planets are great. They allow us to learn an awful lot about the star, about the planet. There's also another thing that we can do, and this is a slide that I've pinched from one of our Open University Astronomy modules, and if you want to learn more about stars and planets, this is the very subtle sales message: take an OU degree, because we teach all of this and it's all great stuff. One of the things that we can do with light as physicists is we can use it to learn about composition, and Dave has already told us how you can do that with X-rays through X-ray fluorescence. But the way that astronomers quite often use is if light is being filtered through a gas, then the atoms in the gas will select out particular narrow colors of light and absorb them. And so that's what's going on across the top of this slide. The light is shining through a gas, and the atoms in the gas are selecting out their own spectral lines. Each chemical element has its own sort of fingerprint of spectral lines. So as astronomers, by looking at light which has been filtered through a gas, we can tell what the chemical composition of that gas is. So without going there, without taking a sample, we can learn about the chemistry. And this was actually how the chemical element helium was discovered. It was discovered in the atmosphere of the sun by astronomers before anybody realized that helium was here and present on the Earth. So this is a really nice technique that astronomers use a lot to know what things are made of. And you can apply this to transiting exoplanets. So this is a zoom in. Again, the black sort of segments of circles is the silhouette of a planet that's crossing its star. And if that planet has an atmosphere that's translucent, then actually, at those exact colors of the light being absorbed by the chemicals in the atmosphere, the planet will appear a bit bigger. So by measuring a transiting exoplanet and spreading the light out into its component colors and measuring how deep it dips at each color, you can actually work out the composition of the atmosphere of the planet, even though you can't directly see the planet. And this is stuff I think is just really, really exciting. And I sort of learned quite a lot about my own psychology when exoplanets were discovered. Because until exoplanets were discovered, which have so much scope for the imagination, I thought planets were quite boring. But now I think planets are absolutely fascinating. So this is one of the things that we can do, and I'll come back to related things later in the lecture. But there was a particular example of this in 2003. Somebody pointed the Hubble Space Telescope at the exact wavelength of the strongest spectral line of hydrogen, which is the most common chemical element in the universe. And what they found was, rather than about a 1% dip in the light from the star, which is caused by the opaque planet itself getting in the way, there was actually a 15% dip at this precise color where hydrogen absorbs. And that tells you that this planet is actually surrounded by a whacking great cloud of hydrogen. And I saw this publication in Nature, and I just thought, this is just too exciting to ignore. So that was the point that I turned my back on my previous research field and decided exoplanets were for me. And I've never looked back. So what I did was I led the Open University into the Super WASP collaboration. And since Josie wants to know what that is, the super is just because it's really good. And WASP stands for Wide Area Search for Planets. And this was a large UK collaboration involving all of these institutions and dozens of people. And it brought people together into an exciting new field. And it was sort of a plucky UK low-budget project, and it's been immensely successful. This is another view of one of our facilities. And those lenses, what look like the little telescopes there, those are actually Canon camera lenses that were designed for theatre photography. And they'd all been discontinued by Canon with the onset of digital photography when they needed new lenses to work with CCDs rather than photographic films. And they'd been remaindered and sent to Korea. So as one of the few women who was involved in WASP in the early days, I got the shopping mission. And so I purchased most of those camera lenses on eBay using our grant funding, which was a little bit nerve-wracking because this was in the early days of e-commerce. So I bought all of those lenses from a very nice man in South Korea who I never met, but he kept up his side of the bargain and we sent him the money. And WASP has been an incredibly successful collaboration. It's still going. It's discovered about 200 transiting exoplanets now. And this is a family portrait album from the early days. So you can see here our first 15 planet discoveries, which are imaginatively named WASP-1 to WASP-15. And what you can see in these thumbnails is a cartoon which represents the size and the color of the host star in color, and the size of the planet. So the size of the planet you can see by the size of the black dot, which indicates the planet is a transiting planet. And then I hope you can also see the sort of the line which indicates the planet's orbit. So of all of these planets, one of the most extreme is WASP-12, which is third from the top on the right-hand side. And that is in a very, very, very short period orbit. So it orbits round a very bright star with an orbital period of just over 1 day. So it's extremely close, it's extremely irradiated, and it's sort of being baked alive. And you can see that that black dot is actually bigger than the other black dots. So this is one of the largest exoplanets that we've found. So I'm now going to move into the main project that I'm going to tell you about, which was inspired by work that I did on WASP-12b. And this project is called the Dispersed Matter Planet Project, and it's a project that I conceived and led, and we've just got our first results, and we're really, really very excited and chuffed about the whole thing. So this again is that thumbnail of WASP-12, so you can see there in the blue line just how tight that orbit is. The planet is only about 1 stellar diameter away from the surface of the star. It really is being baked alive. And the graph on the right-hand side, on the x-axis, is irradiating flux. So that's just how much light from the star is baking the planet. And on the vertical axis is the size of the planet. And in the open circles are plotted all of the exoplanets that we knew back in 2009 when we found WASP-12 using SuperWASP. And you can see they all cluster together, except there's one point in the top right-hand corner, and that's WASP-12. So you can see that's a bit extreme. So I thought, gosh, that one's really interesting. It's really being baked alive, and it's much bigger than the other planets. And those two facts are related. The amount of heat it's collecting is causing it to expand. And so it's a very large planet. And since I'd done my shopping mission, I was given the privilege of being able to lead the Hubble Space Telescope follow-up observations of this particular star-planet system. So we pointed the Hubble Space Telescope at WASP-12 in the ultraviolet, and the graph on the left-hand side shows a zoom in on what we saw when we spread out the ultraviolet light from WASP-12 into very fine wavelengths, and then vertically is just telling us how much light we're getting at each of those very narrowly defined colors. So WASP-12 is plotted in black, and you'll see that the overall shape of what you can see in that graph there is like a W. For WASP-12, the W, the two bottom bits of the W, intersect 0. So there are two narrow colors there that if we looked at that star, we would see absolutely 0 light, even though there's a star there. And every other star in the galaxy, as far as we knew at that point, had the sort of behavior that you can see in the red, green, and blue lines, where instead of going down to 0, at the bottom of the W, you get a little peak. And that's an inevitable consequence of the structure of a star like the Sun, which is burning hydrogen to helium at its core. You always get that little emission peak at the bottom of that W. And that was missing in WASP-12, making the star that hosts this very odd planet completely unique, as far as we knew in 2012. So we developed a hypothesis to explain that, and it seemed unlikely to me that the star would be unusual in its structure and also independently have this very unusual planet orbiting around it. It seemed much more likely to me that those two very unusual properties were causally related. One of them is causing the other. And so I developed this picture that, in fact, what's going on is that the planet, which is being baked alive and we know is very large, is actually losing mass. And that mass is forming a shroud of gas which completely surrounds the star, so that when we're looking at the star, we're actually looking through a gas shroud which consists of material that has been dispersed from the very hot mass-losing planet. And that absorbing gas imprints clues on the starlight. And the first clue that we saw was that that graph goes down to 0 at the bottom of the W. So the absorbing gas imprints clues on the starlight, and that absorbing gas clue indicates that the star hosts a mass-losing planet. The mass-losing planet is feeding the gas shroud, and we're looking through it, and that imprints a clue on the starlight. So this, I thought, could potentially give us a very quick and easy way of identifying those stars which are hosting these very extremely hot mass-losing planets. So I thought what we should do is look at all of the bright nearby stars to see which one have similar clues to WASP-12. So that's what we did. Now, as I said earlier, giant planets are quite easy to find, and bright nearby stars are what astronomers like to study, everything else being equal. So I expected that all of the giant Jupiter-like planets around bright nearby stars would already have been discovered. So I thought this clue would give us a shortcut to finding low-mass, small, rocky planets orbiting bright nearby stars. And having watched Star Trek as a child, I'm much more interested in those low-mass, rocky planets that we could potentially walk around on. So this was my hypothesis, that actually we could use this clue to find some really interesting objects. And then the other thing, just like when planets form, angular momentum suggests that the gas that's being lost should stay in a disk that's concentrated around the orbit of the planet that's losing the mass, which means that we should actually, if we see that clue, be looking at the system edge on, so that we're likely actually to be finding planets that are transiting. As I hope I convinced you earlier, the transiting ones are special. Those are the ones that we really want to find. So that was the hypothesis. So now I'm going to tell you what happened when we tried to apply that. So what we did was we, first of all, found a way of comparing the spectra of all of the bright nearby stars in a way that sort of tells us which one has the clue that there's absorbing gas. So you don't really need to worry too much about the details, but what's plotted on the y-axis here is how much light there is that's sort of peaking up where that W went down to 0 in WASP-12. The yellow squares on this graph are all stars that we already know that host transiting Jupiter-sized planets, and the very bottom yellow dot over towards the left-hand side of that graph corresponds to WASP-12, which, as you saw earlier, is very extreme and does everything more than any other similar planet. And the x-axis, I should probably say, just spreads the stars out so you can see where they all are, and they're not all plotted on top of each other. But the x-axis is just how massive the star is, or equivalently, what color it is. The red line corresponds to what you would expect to a star like the Sun, which is very, very magnetically quiet. And there should be no main sequence stars like the Sun burning hydrogen to helium at their core, which lie below the red line intrinsically. So WASP-12 and the other yellow dots, we know, host mass-losing planets. And we looked at about 3,000 stars, and those are all the blue dots, and we plotted them on this graph, and lo and behold, 39 of them lie below that red line. So those are showing the clue that there is a mass-losing planet present, orbiting around that star, that we haven't detected yet. And for the reasons that I told you, my hypothesis was that these are actually low mass, probably rocky, probably transiting planets. So these are potentially very, very interesting objects to find. So we found 39 targets, and then we went to look for planets orbiting around them. And this is the method that we used. So just like the transiting method, we're using the starlight to find the planet. And you may think that planets orbit around stars, but actually from the point of view of physics, the planet and the star are both masses, and they both obey the laws of physics. So the planet and the star actually are both in orbit around the common center of mass of the system. So as you can see there on the cartoon, the star is doing a little orbit because it has almost all the mass, while the planet does a big orbit. And the rainbow-colored band at the bottom shows you how those spectral lines, which arise because there are chemicals in the stellar atmosphere, move backwards and forwards due to the Doppler shift as the star responds to the gravitational pull of the planet and goes around its orbit. So this is the so-called radial velocity method of discovering planets. So we're looking for very small motions of the star indicated by that Doppler shift, which we can see in the starlight. So we tried to apply this method to our 39 bright nearby stars to search for our low-mass, rocky planets that are very close into the stars and being heated to the point that they're losing their volatiles to form a circumstellar gas shroud. And this is where we did the work. This is the European Southern Observatory in Chile. It's a mountaintop called La Silla in the Andes. And on the left-hand side, there's a photograph I took at sunset, which sort of gives you a snapshot of just how breathtakingly beautiful it is to be there. And then the main picture is the control room, which has actually been the place where most of the radial velocity planets that we know of has been discovered. And you can see from the control room, you get a lovely view of sunset, which is invariably beautiful in the Andes, but being a scientist isn't all fun and glamour, so actually we spend most of our time with the blinds shut, staring at those two computer screens, working very hard, but we try to always enjoy the sunset before the night's work starts. And so just to remind you, what we were doing was looking at those 39 blue dots that lie below the red line, searching for low mass, short period rocky planets in orbit around those stars. And I hope this is probably not that much of a surprise since I'm showing off about it, but we did actually find them, which has been the most thrilling thing of my career, actually. So this is our poster child discovery. So what is plotted along the x-axis here is time in days, and all of the colored points in the upper graph are our measurements. And so you can see we've been back to the telescope several times. Our measurements span about 2.5 years. And what we've discovered is 4 or 5 low-mass, rocky planets orbiting this particular star, which we have renamed DMPP1. So we're staking our claim on it because we've done some original work to say this is a special system because it shows these clues, and we found a system of 4 or 5 rocky planets which are causing the star to do quite a complicated orbit because there's several planets orbiting around it, just as there are several planets orbiting around the sun. So its motion is a superposition of its reaction to all of those different planets' pull. So you get this complicated, jiggly shape due to the 4 or 5 planets that we've discovered. And these are the people that did the work. So here we are looking sort of quite geeky and smug because we've found things. So that's me in the middle. John Barnes is a postdoc who's done a lot of the technical work. And on the right-hand side is Daniel Starb, who was a PhD student working with us. And he's now gone to work in industry, and he's making plasma rockets to go exploring space more directly. So we were the people that were responsible for most of this work. And one thing that we like to show off about is that this was a very efficient way of finding planets. Because we knew exactly what we were looking for from the clue and the logic we applied, we actually were about 2.5 times more efficient than the nearest comparable discovery. So this is quite nice. It's always good to use telescope time efficiently because astronomers always have more things they want to learn about than there is telescope time available. So this is, again, an artist's impression. This is not what we saw, but we have a system of 4 or 5 planets, at least one of which is losing mass and forming a circumstellar gas shroud. And if that dispersed gas is in the orbital plane, then transits are likely, and we'll be able to measure the size of those planets. Handily, NASA has launched a really great space telescope called TESS for measuring transits, and we do actually have a marginal detection of a transit in this system at a depth of less than 100 parts per million. So this is really high precision work, and we're not completely ready to claim this, but we think we might have found a transiting planet in this system, meaning that it's exactly lined up so the planets cross in front of the star from our point of view. This is our second discovery, and this one was a little bit of a surprise. As I said, I thought that all of the giant planets would already be known orbiting these bright nearby stars. And this is actually a giant planet about the mass of Saturn. And as you can see here, this isn't such a pretty graph as the first one that I showed you. There's actually an enormous amount of scatter around this motion of the star in response to the gravitational pull of the planet. And that's because this star is not well behaved for doing this very precise Doppler shift work. And in fact, what's going on is that the star is pulsating. So the star itself is wobbling, which makes it more difficult to discover the planet. But because we had the clue in the starlight, we persisted and found this Saturn mass planet where other people had looked and then just given up. So the nice thing about this one is because the star is pulsating, we can get a lot of really precise knowledge about the structure and the composition of the star. So we can actually learn more about the planet because we have very precise knowledge about the star. So this again is a very, very interesting system for further work. And again, if the dispersed gas that we use to find it is in the orbital plane, then transits are likely. So this again is likely to be a very, very interesting system for follow-up. And then finally, this is actually the most interesting of the systems we've discovered so far. So as you can see on the video, what we've got is 2 things, one orbiting around the other in a very eccentric orbit. And we were looking for very small motions due to low-mass planets. And what we found was a whacking great motion due to a low-mass star. So we found a previously unknown star in this eccentric orbit around our target, which was a star that's about 90% of the mass of the sun, and as far as we knew, unremarkable apart from showing this particular absorption signature in the starlight. And what we found was an object that's right at the very threshold for sustaining nuclear fusion to power a star. So the smaller of those two objects is what's called a red dwarf star, right at the very bottom of the main sequence of stars, only just able to sustain the temperatures and pressures to do nuclear fusion and shine like the sun does. So that's an interesting object in its own right and worth further study. However, we did find what we were looking for too. Orbiting the Sun-like star, there is a 2.6 mass planet in about a 7-day orbit, and it's a challenge to see how this particular planetary system formed, because if you've got a binary star where the stars coming very close into each other, that will truncate and disrupt the disk that the planets are going to form from. So this is a very unusual system, and no other binary star system anywhere near this tight is known to host planets. So this is probably, of all of the things we've found so far, the most interesting from the point of view of the astrophysics we can learn from it. So I'm now going to tell you a little bit about the mass-radius composition relationships for rocky planets, picking up on another aspect of what Dave talked about. So as we've already seen, absorbing gas can reveal the composition of the material in the gas through those sort of chemical fingerprints that get imprinted on the starlight. So that's, again, our OU Level 2 astronomy module picture of how that works. Atoms pick out particular wavelengths of light and leave their chemical fingerprint. So here is a graph. On the x-axis, it shows you the mass of planets, and on the y-axis, it shows you the radius of the planets. And the lines which are drawn on the graph indicate what you would expect for the mass-radius relationship for particular compositions. So Dave already showed us Mercury, which has an unusually large fraction of its composition being composed of iron. And the red line at the bottom shows you the mass-radius relationship that you would expect if you built a planet completely from iron, which is the densest material we know of. And so you don't expect to ever find a planet more dense than that red line. And plotted on the graph are the masses and radii of various planets, all of which are less dense than iron. So that's good. And in the bottom corner, you can see Venus and the Earth. And their masses and radii are known really rather accurately, because obviously we can measure them quite easily. And you can see for the Earth and Venus, we can get a good idea of what the composition is from that mass and radius relationship. Whereas for the exoplanets, because we're working with the very dim light from a star, we have much less idea and much less precision on our mass and radius measurements. So those measurements have big uncertainties attached to them and are consistent with a number of different composition models. Now, the planets that we're finding, we're measuring the mass using the Doppler shift of the starlight. For those that transit, we can measure the radius using the transit depth. And by looking at the chemical fingerprints of the dispersed material, we can actually measure the composition as well. So these objects that we're finding in this OU-led project are actually going to revolutionize our knowledge of the galaxy's rocky planet population and allow us to know the mass-radius composition relationship for these planets directly. Just very quickly, Dave told us that rock can't sublime. In astrophysics, we have much more scope for the imagination, and I'm here to tell you that rock can sublime. So this is a discovery from the Kepler mission, and this is an object that's about the size and mass of Earth's moon in a 16-hour orbit around its host star. So it's really, really very, very close to its star, and it's really, really being heated to a very high temperature. And if you heat rock to about 2,000 degrees, it does sublime. And this particular planet is too small to detect, as Dave said. However, its rocky surface is being turned into gas and leaving the planet. And as the material leaves the planet, dust condenses out of that metal-rich vapor. So you actually see a transit of a dust cloud that's entrained in the orbit of the planet. And this gives us some possibilities to actually start examining the mineralogy of this ablating surface. I'm not going to go into the details. However, our discoveries might include some bright nearby examples of that. So we might be able to do some really interesting exoplanet geology, taking what Dave's doing and moving it beyond our own solar system. So these allow detailed study. And the more we find out about our galaxy, the more it resembles the galaxy in Star Trek. And I just find that really, really very exciting. It gets me out of bed and into the office to sit in front of the computer every morning. So finally, I'm going to just quickly tell you a little bit about planets in the neighbourhood. So this is a European project that I'm involved in, involving collaborators mainly in Spain and Germany. In 2016, John Barnes, who works with me, was one of the discoveries of Proxima b, which is the very, very closest exoplanet to the solar system. It orbits a very low-mass star, Proxima Centauri, which you can see on the right-hand side of the graphic, about 4 light years away. And then in 2018, we found a planet orbiting Barnard's star, which is the closest single star to the sun. So it seems as soon as we start looking in detail at the sun's neighbour stars, we're finding planets orbiting all of them. So at the bottom there is the sun, and there's an indication of the Oort cloud. And in fact, the Oort cloud goes actually halfway to the nearest exoplanet. And there's a reason for that. The Oort cloud is low-mass bodies that are entrained by the sun's gravity. And as all the stars orbit around the center of the galaxy, they each have this sort of large cloud of bodies that follow them around. And sometimes, I guess, they probably swap. But the Oort cloud goes halfway to the nearest exoplanet, which I think actually offers some possibilities for exploration. So rather than going on a generation ship to the nearby exoplanets, we could possibly hop from rock to rock and get there more slowly and gradually. That would be a long-term project. I think you would need tens of thousands of years to do that, but perhaps we could do that. And we do live in exciting times where we can actually think about things like this.